Hello again, and welcome back to this third and last part of Lecture 7. In this one, we will pivot a little bit away from the stars and turn our focus to the ISM of the Milky Way and its various phases. The ISM in the Milky Way consists mainly of hydrogen with some other elements mixed into it, and it consists of multiple phases, which each has its own temperature, density, and so on. So we can try and go through them one by one. The molecular gas we have talked about before is the coldest and densest gas, and these clouds are the main reservoirs from which the stars are forming. These typically have temperatures on the order of magnitude of 10 Kelvin. They're really, really cold. They have densities of more than 100 molecules per cubic centimeters, but the densest star forming of these clouds have densities that are yet even higher. And the total mass of molecular clouds, molecular gas in the Milky Way is about 10 to the 9 solar masses. So about 1 billion solar masses, but it is still a quite relatively modest fraction of the total gas mass of the Milky Way. Then we have what we would call the cold neutral medium, or this is mainly atomic hydrogen at low temperatures. This has a temperature of about 30 to about a couple of hundred Kelvin, has a density of about 30. So this is like not a very accurate number, but a typical number of about 30 per atoms per cubic centimeter, and a total mass of this gas of around 2 times 10 to the 9 solar masses, so about twice as much as the molecular gas. Then we have the warm neutral medium, which is located closer to where stars are forming and so on. This neutral medium has suddenly a much higher temperature of up to about 8,000 Kelvin. It has a lower density, about 1% of the density of the cold neutral medium, but about the same total mass as this. Then we have the H2 regions. These we have talked about before. They're these dense and very highly ionized regions around where young stars have just formed. These have temperatures up to 10,000 Kelvin, and they can have densities that are ranging wildly. As you can see here, this is not a typo. They can range all the way from about 10 electrons per cubic centimeter and up to tens of thousands of electrons per cubic centimeter, with typical values lying from around a few hundred electrons per cubic centimeter. The total mass of H2 regions in the Milky Way is about 10 to the 8 solar masses, so it's relatively modest. On the other hand, when it comes to their luminosity, they are definitely not that modest. They are very prominent. Then we have what we call the warm ionized medium. This is a more diffuse warm gas. This has a similar temperature to the H2 regions, but a much, much lower density, as you can see, down to like 0.1 electron per cubic centimeter. And it has a similar mass as a similar total mass to the molecular gas. And finally, we have the very hot intercloud medium. This gas is more than 1 million Kelvin in temperature. It is very, very, very sparse. And that also means that its total mass is not very, very large. It is modest, just like comparable to the H2 regions, but it takes up much, much more space because it is so much more dilute. The diffuse phases, that is the cold neutral, warm ionized, and hot intercloud medium together, are approximately in a kind of pressure equilibrium in the Milky Way, whereas the other phases are definitely not. This picture here we have seen before. This is the H1 in the Milky Way. And if you remember the last lecture, you can remember that we talked about how we can use the velocities of H1 to construct a rotation curve of the gas and thereby the Milky Way in general from these. And this is difficult to do for the Milky Way, but it has been done. I don't know if you can imagine why this is actually a good deal more difficult to do for the Milky Way than it is for other galaxies, but it is. But it has been done, and here we have such an attempt at doing this all the way back from 1985. And you can see that the rotation speed of the Milky Way comes up to a maximum of about 250 kilometers per second, to then drop off a little bit and settle more or less on a constant value around 225-ish kilometers per second. If we try to take a slightly more theoretical look at this rotation curve is made up of various contributions. First, in the inner part of what it would look like if the Milky Way were a solid body, which is pretty close to how it actually behaves in these inner parts. So that is around the bulge and the bar. These rotate more or less as a solid body. Then you have this contribution here, which is from Keplerian rotation. So that is how things would rotate if the stars were the only mass contribution that there was. And finally, we have a flat contribution, which is basically what happens if we have a halo of dark matter which continues far, far further out than the stellar mass and the gas mass that we can measure, and is completely dominating the mass in the Milky Way. And as you can see, this flat contribution becomes more and more accurate as we get further and further out. And the Milky Way's mass indeed does get more and more dominated by dark matter contributions. And what you see here in gray is, of course, a slightly prettier version of the measured curve for the Milky Way. Assuming that the H1 gas is in hydrostatic equilibrium and making a few other assumptions, we can show that the density of the gas should follow a Gaussian distribution centered around the midplane and expressed or described by this mathematical expression that we see here, where we have like a Gaussian function scaled by the gas density in the midplane at a given radius. So this is as a function of height above or below the galactic plane, but this value here is then unique for any location within the galactic plane and the gas immediately above, or the regions immediately above and below it. And also, as you can see, Z here is the height above or below the disk, and H gas is the gas scale height. If we assume a flat rotation curve, this simplifies, of course, a bit, and we can get the scale height as this formula that we see here. And in the solar neighborhood, that scale height is about 135 parsec. That was it for today's lecture. The discussion questions that I would like you to think about until we meet are as follows. Question A says, discuss the difference of the thin and the thick disk of stars in the Milky Way. How do you think that the thick disk formed? And the second question says, B, discuss how the molecular gas in the Milky Way is distributed spatially. Why do you think the structures are so inhomogeneous? What are the implications for star formation of this? And that was it for today. Thank you for staying with me this far. And as always, I am looking forward to seeing you in the next one. Bye for now.